Well, hello, good people. Today we are talking about the law of conservation of energy. Now, when we talk about the law of conservation of energy, it turns out that there are actually really deep down two laws of conservation of energy. Or there's one law. Wow, okay. There's one law that we can break down two ways, and let's take a look at that law. Here it is. The law of conservation of energy, you have heard before, is that energy cannot be created or destroyed. This means the total amount of energy in the universe always stays the same. And this is what I call like the big time law of conservation of energy. Big time. Oh, okay. Well, anyway, this is what we call the big time law of conservation of energy. Physicists will hold on to the big time law of conservation of energy very, 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 very seriously. We say that you can't just create energy out of nothing. You can't take energy that already exists and just get rid of it. What you can do is you could transfer it, so you could move energy from one object to another object. You could change its form. You could turn it from kinetic energy into potential energy, for example. But what you can't do is you cannot create new energy out of nothing. You cannot destroy energy that already exists. In other words, the total amount of energy in the universe always stays the same. That's the first big time law of conservation of energy that applies to literally the whole universe. But then we have a smaller, more specific law of conservation of energy that applies to systems. And here's that law of conservation of energy. That law of conservation of energy says if only conservative forces do work on a system, then energy is conserved within that system. Here's the difference between these two. The big time law of conservation of energy says that energy in the whole universe can't be created and we can't destroy it. It's always going to be whatever it is. The number or the total amount of energy in the universe is fixed. But then the second law of conservation of energy, the small time law of conservation of energy, says, hey, if I have a system, like a collection of objects, for example, if I have a system, then all of the energy will stay in the system and it won't leave the system as long as only conservative forces do work on the system. All the energy in the system will stay the same, so energy will not leave the system. Now, this begs the question, what is a conservative force? And yes, of course, that is an essential concept for understanding the second tiny law of conservation of energy. And here's our definition of a conservative force. A conservative force is a force that whose work is path independent. My definition here says, I'll move my face out of the way. My definition here says that a force is a conservative force if the work that is done by the force moving an object between two positions is independent of the path of motion. Let's take a look at an example. I have some examples here and some non-examples here. Let's take a look at those first two examples. We'll talk about gravitational forces and about friction. Here, a force is conservative if the work done by the force is path independent. Here's what that means. We'll use my physics textbook again, and we'll use this eraser. Okay, suppose that I have this eraser here, and I push it across the book here, push it along this way, and then push it back here so that it ends up at point B. So here's point A where it started, here's point B where it ends. Sorry, I'll make this bigger. You're like trying to look at a teeny tiny screen here. That's just not convenient. Okay, here we go. So, suppose that the eraser starts here at point A, and then it takes a path where it goes bloop, 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 and it ends up back here at point B. Do you agree that friction does work as this little eraser moves around the book? Because friction is going to be acting on the eraser for a certain displacement. So there's a force that happens for a displacement. We say that that force does work. So friction does work. Here's a question. Let's suppose that there are two routes to get from point A to point B. The question is, when does friction do more work? If I take path 1, bloop, 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 or if I take path 2, bloop, just like that. Well, you would say, Miss Wilson, Friction does way more work when you take path 1. Why? Because you go a longer distance and friction is acting for that whole distance. So friction will do more work going this way than it will going this way, just because the path is longer. This is a non-conservative force because the amount of work that it does depends on the path that you take between point A and point B. We can contrast this with something like gravity. You'll remember from the lab that we just did that gravity is a force that does the same amount of work no matter the path that you take to get there. Let me show you what I mean. In a lab on Friday, you had, or I guess it depends on when you're watching this video, but in a lab, we had a situation where we had a block here on a ramp. And then, sorry, I gotta move my thing here. Get out of the way, thing. Yay! Okay, so you had a situation where you had a block here, and you did, oh no, I don't like that, and this is in the way. Ah! Oh no, don't do that. Don't do any of the things. Don't do, no, okay. Okay, sorry everyone. I just do deeply apologize. Okay, here we go. All that for an arrow. What we did is you pulled this block, you pulled this block up all the way. This is just incredibly disappointing. I wish I were better. I really do wish I were better. Okay, you pulled a block up. Ah! If it wasn't so slow to load, then maybe it would be a lot easier. Okay, I'm landing with that. That's fine. You pulled a block all the way up a ramp like this until the block ended up right here. And that took a certain amount of work. And then you measured how much work would happen, how much energy would get transferred if instead of going up the ramp, you took the block straight up like this. Now what we did in this lab is we eliminated friction on the ramp, and you took a look at how you did that, but we eliminated friction on the ramp so that the only force that you were working against was gravity. So you were working against gravity this way, and you were working against gravity this way. And what we found is that the amount of energy transferred here, the amount of work done in pulling it straight up the ramp versus lifting it up, was exactly the same. You had the same energy transferred if you went from here to here as if you went from here to here. In other words, if point A is at this height and point B is at this height, the amount of work that it takes to get from point A to point B is the same, regardless of whether you go straight there or slide the block along the floor and then slide it up a ramp. This is why we say that gravitational forces are conservative forces, is because the amount of work done by gravity is the same whichever path you take between point A and point B. So gravitational forces are conservative forces. Friction depends on your path. Electric forces are conservative forces. The electric force does the same amount of work no matter which path you take, as long as you start and end at the same point. Elastic forces, which is like spring forces, those are the same way. They do the same amount of work as long as you start and end at the same point. But then some examples of things that don't do the same amount of work, even if you start and end at the same point, is things like friction or tension or pushing or pulling. If I were to push something around a room and I push it the long way versus the short way, I do more work if I go the long way versus if I go the short way. So that would be an example of a non-conservative force. Now, here's the main idea about a conservative force, is that if only conservative forces do work on a system, then energy is conserved within that system. If only these types of forces, like gravitational forces or electric forces or elastic forces, if only those kinds of forces, if only conservative forces do work on a system, then energy will stay inside the system. The energy might change forms, so it might go from being kinetic energy to potential energy or vice versa, but it'll still be in the system. Forces like friction, tension, air resistance, or pushing and pulling, if those forces act on a system, they will take energy out of the system or they will add energy into the system. So the total amount of energy of the system won't stay the same. So if only conservative forces do work on the system, the energy in the system stays the same. It doesn't leave. It might change forms inside the system, but it doesn't leave the system. If any one of these kinds of non-conservative forces does work on a system, it will take energy out of the system or put energy into the system. Let's look at an example of how the law of conservation of energy could be used to solve a problem. If this will load. Okay, this is Mike. And for about a whole week now, Mike has been working up the courage to jump off the high dive. Now, when Mike stands at the top of the diving board, if he jumps off, the only force acting on Mike will be the force of gravity. And gravity is a conservative force. So if only gravity is doing work on Mike, Mike's total amount of energy won't change, or the total system of energy, the Mike Earth system, won't lose any energy or gain any energy, but it might change forms within the system. Here's where we need to start. We would say that the total amount of what we call mechanical energy, and this goes back to what we learned a few days ago about mechanical energy, that mechanical energy is just a combination of all of the potential energy and all of the kinetic energy. So this is what we call, sometimes I'll write it as E total, sometimes I'll just write it as E, sometimes I'll write it as E sub M for mechanical energy. But this is the total amount of energy in a system. The total amount of mechanical energy is going to be all of your potential energy plus all of your kinetic energy. Well, if Mike here is going to be falling under the influence of gravity only, which is a conservative force, then the total amount of energy in the Mike Earth system will not change. In other words, the change in energy will be zero. Let's take a look at what this looks like. When Mike is standing up here right before he steps off the diving board, he does most definitely have some gravitational potential energy. Judging by the size of our high dive here, I would say Mike's gravitational potential energy is probably something like 10,000 joules while he's up here. But when he starts at the very, very tippy top, he has no kinetic energy because he's not moving. Then Mike bravely steps out off the diving board and he begins to fall. And as he falls, he goes down, 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 down. And so his height becomes less and less and less and less and less. And since his height is less and less and less and less, he has less and less and less gravitational potential energy. But he's also getting faster and faster and faster. And so he has more and more and more kinetic energy. Hey, I bet you could guess. If Mike starts at some height, which we'll call H initial, and he's going down to some H final. Whoa, sorry, I used a not there. That's what we use in AP Physics, is we call it not, but let's call it initial. Oops, ba-doop. Okay, suppose that he starts at some H initial, and he's going down to some H final. Well, along the way, when he's halfway down, when he's accomplished half of his change in height, could you guess down here what would his gravitational potential energy be and what was his kinetic energy be? Well, you say, sure, Miss Wilson. His gravitational potential energy at this point would be 5,000 joules. And his kinetic energy at this point would be 5,000 joules. Because as he falls, he has less and less and less potential energy, more and more and more kinetic energy. When he's halfway, he has half potential, half kinetic. And then by the time he gets all the way down to the bottom, when he gets down to his swimming pool, at the bottom, we say that he would have no potential energy, no gravitational potential energy, but he would have all 100% kinetic energy. All of his energy would have become kinetic energy. Could you give a guess as to what kind of gravitational potential energy he would have here, 3/4 of the way down? And how much kinetic energy he would have? And could you give a guess as to how much gravitational potential energy and kinetic energy he would have at this point, 1/4 of the way down? Did you say that down here he would have more kinetic energy than he would have potential energy? 3/4 of his energy would be kinetic energy. So he would have 7,500 joules of kinetic energy and 2,500 joules of potential energy. Up here, most of his energy is still potential, but he's gaining some kinetic. So he would have 7,500 joules. That's 3/4 would be potential energy, and 1/4 would be kinetic energy. Here's what you can see is that the total amount of energy in the system never changes. E total, which is the potential plus the kinetic. Do you see that the whole way through it always adds to equal 10,000? But it does change forms. So at first it's 10,000 all potential and 0 kinetic. Then gradually potential goes down, down, down as kinetic goes up, up, up. And then it gets to the end and it's all kinetic and none potential. The way that we write this sometimes is we say that since delta E equals 0, then the change in potential plus the change in kinetic together equals 0. Check it out. Between here and here, the potential energy lost 2,500 joules between here and here. So that would be negative 2,500, but between here and here, the kinetic gained 2,500, so that would be positive 2,500. So you'd have minus 2,500 plus 2,500 equals 0. In other words, however much potential energy you lose, that's how much kinetic energy you gain. Or however much kinetic energy you gain is how much potential energy you lose. Or however much potential energy you gain is how much kinetic energy you lose. In other words, these are going to cancel out. The amount of energy you have in one place is just going to transfer to the other place. That's a quick conceptual look at conservation of energy. What we're going to do next is we're going to do a little mathematical look at conservation of energy. Let me go ahead and get that slide pulled up here. One sec. Okay, now here's what happened to our dear friend Mike. Actually, I'm afraid... Okay, good. I was afraid my pen wasn't going to work. Here's what happened to our dear friend Mike. After Mike climbed up the ladder and went to the top of the diving board, he was going to do another dive when sneakily Sarah climbed up the ladder behind him and snuck all quietly behind him, just like so. Now, Sarah was Mike's younger sister, and if you've ever had a younger sister before, then you know exactly how this is going to go. Or honestly, if you have a sibling of any kind, you know that Sarah comes up behind Mike, and that Sarah gives Mike a wee little bit of a push. Giving Mike, are my pens here good? Okay. Giving Mike an initial velocity of, let's say, 2.5 meters per second. Now, we're going to need to lengthen the size of our swimming pool a little bit here because Mike was not anticipating a projectile motion sort of situation. But now, oh, wow, that was so much more dramatic than I wanted it to be. Okay, try again. Go back, go back. Everyone just relax. You got it. You got it. Okay, move. You can do it. Yep, I know it's a lot. Okay, great. So, we're going to need a little bit of a bigger swimming pool here, so we'll extend this out just a little bit to make sure that the water is there to catch Mike. Because now Mike is in kind of a projectile motion sort of situation. And he's going to go falling through the air like this until he lands in the pool below. Now, as Mike is flying through the air, he's saying, this is not what I was anticipating. And I was thinking actually that I was going to be in a nice, like, starting out not moving kind of situation, but he says that's not the situation I'm in now. So I would like to do some quick math. So Mike starts thinking, and he says, okay, well, gravity is still the only force that's acting on me, which means energy is still being conserved. So the total amount of energy in the system is still going to be the same the whole time. So however much energy I started with is how much energy I'll end with. Well, then he says we can break down that delta E into two things. He says we could break that down into my change in kinetic energy and my change in potential energy. And here's what he says is he says, okay, well, as my potential energy is going down, my kinetic energy will go up. And so the total change here will still be equal to 0. Then he says, let's break these down into finals minus initials. So he says I have K final minus K initial plus UG final minus UG initial. And he starts to look at each of these and he says, okay, he says, actually, let's start with our finals. He says, K final, I will most definitely have some final kinetic energy right before I hit that water. UG final, he says, I'll actually have none potential energy by the time I get to the bottom. So that will be 0. Then he says UG initial. He says, I definitely started with some initial potential energy. And then he thinks about K initial. Did Mike start with kinetic energy? Yes, because of Sarah. Sarah gave him an initial push. And so because of that initial push, he did start with some kinetic energy. So the only thing that we can say is 0 here is UG final. Okay, now take a look. In for each of these, we're going to replace it with equations that we know. For K final, I'm going to write in 1/2 mv final squared. For K initial, I write in 1/2 mv initial squared. For UG initial, I write in mgh initial like this. And I say that that's all equal to 0. Now, Mike is feeling pretty good about this situation now because he feels that he can calculate his final velocity. Here's why. First, when you rearrange to find the final velocity, you get 1/2 mv final squared on this side, and then we're going to move these two terms over to the other side. So you get 1/2 mv initial squared plus mgh initial is equal to 0. First thing to notice, oh gosh, no, it's not equal to 0 because I just rearranged that equation. That's embarrassing. Don't listen to me. I'm crazy. Okay, there we go. Yay. First thing to notice here, do you see that the masses all cancel out? Which means that the mass of Mike has no bearing on how fast he'll be going when he gets to the bottom. Doesn't that make some sense to you? Don't we say that all things that are accelerating under the influence of gravity only accelerate together? So a paperclip or a rock or a pencil or an elephant would all fall with the same speed, and they would all have the same speed when they get to the bottom. So that feels good to us. Here's the next thing. When we rearrange, we get the V final is equal to the square root of, multiply both sides by this 2 to get rid of the 2, and then we'll square root both sides, as we've already done, to get rid of the square root. When I multiply this by 2, I get V initial squared. It's going to cancel out with that 1/2. Then when I multiply this term by 2, I get 2 times GH initial. Now, Mike's feeling pretty good about this situation because he knows that Sarah pushed him with an initial velocity of 2.50 meters per second. And he knows that the initial height of the diving board, well, as he's looking at it as he's falling, it appears to be, and you can see this totally based on our scale, it appears that his change in height is going to be 100 meters. So he started about 100 meters above the ground, and he's going to end down at the ground. So we write this, when we plug in numbers, as for our initial speed, it's 2.50 meters per second, plus 2, squared, plus 2 times 9.81 meters per second squared, plus his initial height is going to be 100 meters. And we can plug that all into our calculator, which I forgot my calculator, so give me 5 seconds. 1, 2, 3, 4, 5. Oh gosh, I really didn't make the cut, but that's okay. Okay, here we go. When we type this into our calculators, we get 2.5 squared plus 2 times 9.81 times 100. Then square root that whole thing, and we get about 44.3. Nope. Sorry. Wow. Eraser. Yay, yay, yay. 44 point. Nope, that's still an eraser. Come on. 0.4 meters per second, which is just around 100 miles an hour when he lands in the swimming pool. Huzzah! Now he is feeling very brave and he has no fear because he knows exactly how fast he'll be going v final when he gets to the bottom. Hey, note here, students. Do you see how this is a projectile motion problem? And we could have done this in the past using projectile motion. And if we did it using projectile motion, I actually never asked you to find v final when we did projectile motion. Why? Because your final speed would have a vertical component and a horizontal component. And that gets really very complicated because you would have to find both your vertical component and your horizontal component, and then you would have to relate them together Pythagorean theorem style, and so it really would be kind of a messy problem. But conservation of energy, because energy is just energy, it doesn't care about direction. And so it makes two-dimensional problems much, much easier to do in terms of energy than to do it in terms of, what am I talking about? Wow, sorry. In terms of kinematics. I got all distracted in my brain. I was thinking about rotational mechanics. Okay, let's go ahead and look at one other problem. I'm just going to set up this problem for you, and then you can finish it out on your own. This is page 177, number 4. So take your textbook and flip it open to page 177. Huzzah! We're going to take a look at page 177, number 4. That was just somewhat disastrous, but I think it's all going to be fine. Okay, page 177, number 4 says, an Olympic runner leaps over a hurdle. If the runner's initial vertical speed is 2.2 meters per second, how much will the runner's center of mass be raised during the jump? Okay, let's draw a quick picture of this situation so that you can kind of see what we have going on here. So here you have I'll draw the hurdles. A true story about my childhood. When I was but a child in elementary school, one of my friends in elementary school, Nadia, jumped over the hurdles and fell and broke her arm. And before that I could do the hurdles, and after that I could no longer do the hurdles. I think that I now have a traumatic response to hurdles after seeing Nadia break her arm. But really, like truly, I can't do hurdles at all anymore. So that's true about my life. Okay. Here we go. Olympians are not so. They did not see their friends break their arms when they were in 3rd grade. And so they have no fear when it comes to going over the hurdles. And so here you have an Olympian going over a hurdle. They have what they're going to do when they approach the hurdle is this is basically going to be a backwards of Mike sort of situation. They're going to be going forwards, but we're going to ignore that horizontal component of their velocity, and we're only going to focus on the vertical component of their velocity. When they jump both forward and vertical, but this says that they have an initial vertical speed of 2.2 meters per second. Meters per second. And this Olympian is going to then make their way up over, wait, I can draw a hurdler. Pew. Oh gosh, erase, go back. Okay. Ah, yes, a picture of Grace. Okay, here is the Olympian clearing the hurdle like this. The question is, how much will the runner's center of mass be raised during the jump? What we're looking at here is we're looking for how much their center of mass will be raised. Now, the reason why we chose their center of mass is just because that's an easy location to choose. We had to choose some part of the runner to change their height, and so instead of saying the top of their head or the bottom of their feet, we just chose the middle. So if this is where the runner's center of mass is, this is where it starts. That's a terrible dotted line, but you get the idea. This is our H initial. And then this is where the runner's center of mass ends. This is H final. And we are looking for this delta H right here. Okay. The idea would be that when the runner gets to the top of their path, their velocity in the y direction will be 0. So they could just say, we could say here that their final velocity would be 0 up at the top of their running path. Now we can use conservation of energy because while they're in the air, the only force acting on them will be gravity, which is a conservative force. So we start with conservation of energy. We would say that their total change in energy is going to equal 0. And we say that that energy can be broken down into potential energy and kinetic energy. Now, I'm going to leave, for this example, I'm going to leave this delta UG as a delta here. That's because I'm looking for a delta H, so I don't want to break it down into a final and initial. Instead, I'm just going to call it mg delta H. But I am going to break down this delta K into a final minus initial because that's going to be helpful to me. So I'm going to say K final minus K initial is equal to 0. Now, here's why I break it down is because I know that at the end, this runner is going to have no vertical speed up at the top. So I can say that K final is equal to 0. They are going to have some initial kinetic energy though because they start by jumping. So they start with an initial velocity here. So then I can rewrite this as mg delta H plus, oh no, not plus, oh gosh, wow, that's embarrassing, minus, because we got a minus sign here, minus 1/2 mv initial squared is equal to 0. Now you could rearrange here and solve for delta H. And that's all for today, folks. Today we talked about the law of conservation of energy. Actually, we talked about 2 laws of conservation of energy. One that's like big time, like applies to the universe, and one that applies to how energy leaves or enters into certain specific systems. Then we talked about how to look at potential energy and kinetic energy, and we add them together to create the total mechanical energy. And we looked at some examples to show us how those energies will change when energy is conserved, as long as there are only conservative forces doing work on the system. We looked at how those energies will change, but that the total amount of energy always stays the same, even though the energy might start kinetic and end potential, or start potential and end kinetic. And that is all for class today, good people. I hope you have a wonderful rest of your day, and I'll see you next time. Bye, everybody.